This PowerPoint presentation covers Section 16.1 and 16.2 from our OpenStax textbook. Topics are spontaneity and entropy. Before watching this video, make sure that you have completed the reading guides for Section 16.1 and 16.2 from the textbook. Have your copy of the Chapter 16 handouts ready to take notes on as we work through this section. Thermodynamics is the branch of chemistry that studies the transfer of energy in chemical reactions and processes. It provides the theory that explains what we know about chemical reactions and how and why they proceed in certain directions, but not others. Because thermodynamics is so important, but honestly kind of boring, I like to start off this chapter by listing the overall goals of the material to help keep us focused. The goals of the material in this chapter are to be able to use thermodynamics to predict whether a process will occur under a given set of conditions, and to use thermodynamics to predict and calculate the value of the equilibrium constant for a given reaction at a given temperature. So by the end of this chapter, we will be able to use tabulated data like enthalpy changes and other thermodynamic quantities to determine the spontaneous direction of chemical reactions and values of equilibrium constants. We'll also be able to calculate how the value of the equilibrium constant changes with temperature, something that up to now we've only looked at qualitatively. I'll also now summarize the important laws of thermodynamics. In this chapter, we will be adding two laws of thermodynamics to the one that we already know. Recall that the first law of thermodynamics is that energy cannot be created or destroyed, that the energy of the universe is constant. The second law of thermodynamics states that the entropy of the universe increases in a spontaneous process and remains unchanged in an equilibrium process. The third law of thermodynamics states that the entropy of a perfect crystalline substance is zero at 0 Kelvin. The term that chemists use to describe the natural direction of a reaction or process is spontaneity. A spontaneous process is a process that occurs under a given set of conditions. Sometimes a given process will always be spontaneous in a certain direction. For example, a ball will always naturally roll downhill. However, other times, the spontaneity of a process will depend on temperature. For example, ice will melt if the temperature is above 0 degrees Celsius, but liquid water will freeze if the temperature is below 0. This is one of my favorite images for the idea of spontaneity. Spontaneous means it will happen without a continuous input of energy. In this example, the skier going up the hill is non-spontaneous, but he can get up the hill by expending energy. It's important to note, however, that when a chemist uses the term spontaneous, he or she doesn't mean suddenly or fast. It just means that it will happen in that direction. What governs whether a given process will be spontaneous or not? We can use a couple of examples of processes that we know always only go naturally in one direction to get some ideas. First, we know that a sample of gas will spread out to occupy the whole space available to it. This first picture shows what happens to a gas sample contained in one compartment of a flask. When the stopcock is opened to the other chamber, the gas molecules spread to fill the whole container. This always happens, and if there are sufficient number of gas particles, never the reverse. So one aspect of spontaneity might be that matter tends to disperse. Another example of a process that always naturally occurs in one direction is heat transfer. Heat always flows naturally from a hotter object to a colder one to spread out the energy. So we might also say that a spontaneous process results in a dispersal of energy. To summarize, spontaneous processes result in a more uniform or spread out distribution of matter and/or energy. In the next section, we'll link this idea to probability. Systems proceed in a certain direction because that is the most probable outcome. And we'll define a new thermodynamic state function to quantify this tendency. The thermodynamic function that quantifies the spontaneity of a reaction or process is called entropy. Entropy is given the symbol capital S. The entropy of a sample can be defined as being proportional to the number of different ways in which the particles can be arranged. The proportionality constant is called Boltzmann's constant, K, and the different arrangements of particles is given the symbol W, which are called microstates. So entropy S is equal to K times the natural log of the number of microstates. For systems with a large number of particles, it's difficult to determine the value of W. An alternate definition defines entropy, or the change in entropy, for a system or process to be equal to the heat transferred under reversible conditions divided by the absolute temperature. We will use both of these definitions of entropy in this chapter. Since entropy is a state function, delta S will be equal to the final entropy minus the initial entropy. This slide is from your textbook and shows all the possible ways to distribute 4 different particles into 2 boxes and links the idea of dispersal of matter to probability. There are a total of 16 different ways to distribute the particles. Only 2 of those ways involve having all 4 particles in one box. Notice that the most probable distribution places 2 particles in each box. In other words, distributes the particles evenly as the most probable outcome. This result is even more pronounced when there are a larger number of particles. This relates back to our earlier definition of entropy as S is equal to K times the natural log of the number of microstates. The higher number of possible distributions, the larger the entropy. And we'll see later that processes that increase entropy are spontaneous. The more possible ways the individual particles in a system can be arranged, the higher the entropy. Energy will be dispersed unless there is something to prevent it, because that is the most probable outcome. Dispersal of energy occurs because the probability is much higher that energy will be spread over many particles than it will be concentrated in a few. Concentrated matter also tends to disperse unless there's something to prevent it, because that is the most probable outcome and because it has the highest dispersal of energy. We can use this understanding of entropy to predict the sign of delta S for various physical and chemical processes. In later sections, we'll see how to calculate a number or a quantity for this as well. For now, though, here are some qualitative guidelines for predicting the sign of delta S. The entropy of a gas sample is much larger than the same material as a liquid or solid. This is because gas molecules are more dispersed and therefore have more microstates available to them. Liquids usually have more entropy than solids for the same reason. This means then that the process of melting results in a positive delta S for the system because the entropy of the liquid is greater than the entropy of the solid. Evaporation of liquid also has a positive delta S for the system. Other processes that are associated with a positive change in entropy for the system are the dissolution of a solid solute into solution and increasing temperature. Entropy usually increases when solutes dissolve in a solvent. However, for strongly hydrated ions, the entropy can actually decrease upon dissolution due to the ordering of the water molecules. Entropy increases with the increasing temperature because particles have more microstates available to them at the higher temperature. The increase in entropy with temperature can be explained by the Boltzmann distributions of kinetic energies as a function of temperature. The graph below shows the distributions of kinetic energies for a sample at two different temperatures. Notice that for the higher temperature, T2, there are more possible energies for the particles, so the system will have a higher entropy. For samples at the same temperature and in the same physical state, more complex molecules will have more entropy than simple atoms or molecules. For example, a 1 mole sample of ammonia gas will have more entropy than a 1 mole sample of neon gas at the same temperature. You can think of this as being because the atoms in the ammonia molecule can vibrate with respect to one another, and the molecule can rotate, all of which gives it more microstates. We can also predict the relative entropies of ionic solids. Entropy will increase as the strength of Coulombic attractions decrease. This is because the stronger the ions are held together, the fewer microstates are available to them. The strengths of Coulombic attractions in an ionic solid depend on the charge on the ions. The higher the charge, the stronger the bond. So for example, magnesium sulfide will have a lower entropy than sodium chloride because the magnesium sulfide bond is stronger because the charges on magnesium and sulfide are higher than the charges on sodium and chloride. On the other hand, the strength of Coulombic attractions decreases as the distance between the ions increase. If we compare sodium chloride with sodium fluoride, the bond in sodium fluoride is stronger because the distance between the ions is smaller. Therefore, sodium fluoride will have a lower entropy than sodium chloride. So ionic solids with higher charges have less entropy, and ionic solids with smaller ions will have less entropy. Finally, entropy decreases when a gas dissolves in a liquid because confining the gas molecules to the liquid system reduces their number of microstates. For chemical reactions, to determine the sign of the entropy change, you need to compare the entropies of the reactants and products using the ideas that we've just talked about. In most cases, since gases have such larger entropies than anything else, generally the side of the reaction that has more moles of gas will have the higher entropy. For example, what will be the sign of delta S for the following reaction? Nitrogen oxide gas plus oxygen gas makes nitrogen dioxide gas. On the left side of this reaction, we have 3 total moles of gas, and on the right side, we have only 2 moles of gas. Therefore, the process of going from reactants to products reduces the number of moles of gas, and delta S will be negative. In popular language, entropy is often linked to disorder, and sometimes examples of messy rooms are used to explain entropy, or even more commonly, blamed on entropy. However, this example or analogy is not really accurate. Your room does not naturally become messy unless you actually expend the energy to mess it up. You should now be ready to attempt group problems 1 through 3 in Chapter 16. In the next video, we'll look at the second and third laws of thermodynamics.